Hello again. Today we're going to look at sine, cosine, and tan and waves. We're not looking at triangles. We're looking at ways to understand sine, cosine, and tan. We're looking at what information's held in there. We'll actually show you don't need cosine, tan. And we'll try and look at how important they are. So, you've all seen the triangle, right angle triangle. We can define an angle somewhere. And the hypotenuse, the long side, the opposite to the angle, adjacent to the angle. We can define sine, cos, and tan. What do they actually mean? Well, what we're going to do is we're going to get rid of cos and tan really quickly, show we don't need them. We're also going to show sine is just a cycle. You don't have to get carried away with it. It's just a cycle. What do I mean by a cycle? Well, the universe is full of them. Smooth and continuous change. The Earth's a good example. It rotates on its axis every day. Every year it rotates around the Sun, and the whole solar system rotates around the galactic central point. We'll see sound and light are repeating cycles. There is nothing else but just a cycle to them. And we'll see at higher level we use cycles when we count with complex numbers. Sine first reported in India, we believe, about 1500 years ago. It's been around a long time. They were looking at stars. So what we're going to do, to form a sine wave, all we need is a continuous smooth cycle. So we're going to have a ball going in a circle. It's constant speed, and what we're going to measure is vertical position, just a vertical position, versus time. Okay, so we have y and y. Ball starts there. Sometime later the ball's moved up, so it's moved up and across a little bit in time. Sometime later again, it's moved higher in y. A little later, it's actually gone through 1 and going down again. A little later, it's gone down below 0. A bit later on, it's travelled all the way around to here. It's almost at -1. And it starts to travel back up to its original position. I do this with lots and lots of data points. I get the sine wave. So the sine wave is just something circle. On cycle, we defined as from when it goes back to a repeat position. So we can start here and go to here. Start at 0, we can start here, but it's when it's ready to repeat. It's not half. Where do the triangles come in? Well, if we imagine we wondered about how the ball moved from there to there and what happened with that height, we might draw a triangle in there because we have the radius of the ball, we know the radius of the circle, so we can work out the vertical height. Of course, this is these right angle triangles that we've defined off. Of the interest in the triangle. So let's look at this one. We've got a sine wave. It's caused by the ball starting here going in a circle. Let's start a ball there instead. Start it at y equals 1 and here, and plot it as it goes round. Oh, exactly the same way. Well, it would be. It's just the same circle. Suddenly, it's obviously starting at 1, and mathematicians will tell you it's a cosine wave. I'll tell you it's the same because I drew this wave and I copy-pasted it down there and moved it to the left. Changed it to purple. It's definitely the same wave. And you can define cosine in terms of sine. This is obviously sine. This phase added, subtracted. So that's all we need to do to have cosine. We don't need to use cosine. We could always use sine. If you want more simulation type things, Colorado FET is a really good site for simulations. They'll do much better little circles and things than I can. So, sine and cosine wave is a sine wave shifted to the left. Cosine has no new information. It's useful to pick up just at this point that any wave we think of, square wave, triangle wave, or a piece of music you really like, can be made by just mixing sine waves, different amplitudes, frequency and phase. Okay, obviously you've got to get the phase exactly right, which is why we find phase very interesting. All your musical systems actually just produce sine waves and mix them to make the lovely sound you hear from. I'm only going to give one example of wave mixing just to show how important phase is, but just the one. Here we have two sine waves. Add them up, 0 plus 0, 0, 1 plus 1, 2. We get a wave that goes between 0 and 2, not 0 and 1. Okay? Same sort of wave, really. And of course, when we did this, two balls are moving in phase. We started at 0. And let's look at this one. What we do is we have one ball that starts at 0, one ball that starts at 1 pi radians or 180 degrees out of phase. This gets interesting because this one's going to go positive straight away, like I did, yeah, positive. This one's going to go negative straight away, negative. That's when we add these two up, and they're the same waves, just moved. If we add this wave and this wave, 0 and 0 is 0. Minus 1 and plus 1 is 0. 0 and 0 is 0. Minus 1 plus 1 is 0. Just by phase shifting, we change from a big wave to 0. So obviously phase is really important. If you're a physicist, constructive and destructive interference, this is it. So phase is really only important if there's more than one wave. Okay? Doesn't matter if there's just one on its own, you don't have to worry about it. Measure phase in degrees or usually radians. Radians are better, you'll find that as you go through. So now let's look at the tan function. We said cosine we don't need. When you do tan, it always seems a bit odd. It's not got the hypotenuse in the calculation. It's opposite over adjacent. Tan means tangent. That's what the word means. That's where it comes from, tangent. A line at 90 degrees to a curve. So here we have a circle, here we have a line at 90 degrees. So obviously that radius is at 90 degrees to it. A circle has infinite tangents or sides. There's only one tangent for each angle. Now, tan is its opposite over adjacent in horrible triangles. You can also say it's sine theta over cos theta. Which is sine theta over sine theta. Obviously we can do it in degrees or radians. This is a phase difference to go to cosine. So tan's just another way of looking at the same information. There's nothing in here that isn't sine. Okay, tan's related to how sort of sine changes with phase or time. Sine over itself at a different time. So all the functions can be related to sine and defined by sine. All the trig functions. And all waves, all music, all the light you see, we can build up from different sorts of sine wave. Sine waves are a fundamental wave that anything else can be built up out of. And a mathematician will tell you the waves have to be continuous and single valued, but don't worry about that. Let's look at one of the properties of sine. Let's plot the gradient slope of sine versus time. So we draw lots of lines all over it to find the slope at different times, and we'll plot the slope down here. Now this is where it gets odd. The slope here is quite steep and positive. Yeah, it's there. The slope at the top is 0. It's there. The slope here is 0. It's 0. We look at the gradient of a sine wave. It turns into a cosine wave, which we've already said is a sine wave. So differentiation, or finding the gradient of a sine wave, is a sine wave. This is very odd if you're used to doing differentiation, because most things slowly reduce to 0, which is quite an odd result. Let's look at the other idea. We can integrate a sine wave. We can look at the area underneath. Measure the area at different points and say the area before then. But the thing we do is we have negative areas. So the area to this point here, this time, one cycle is 0. Positive area and a negative area. So we can see the area gets bigger and the area gets smaller. The area gets bigger. And if we plot that out, a mathematician will tell you that's a negative cosine wave. But look at it again, we just shift it along. It's a sine wave. So if you integrate a sine wave, you get a sine wave. Sine wave survives integration. It's quite unusual. So, if we think about any mathematical function, there's only really 3 things we can look at. We can look at a value at a certain point. We can look at the gradient at that point. And we can look at the area under the curve at that point. You do that with sine wave. It's always sine. Whatever you can think of doing to a sine wave, it turns into a sine wave, which makes it quite unusual. Even things like exponentials, and this is a badly drawn exponential. Exponentials relate to a growth with a constant in there, just like constant circles. So you can define exponentials in terms of sine waves. Now the mathematicians might say, which one's defining which, but the two are related. So sine really is an important function. Okay, so sine, some mathematics we look at, is it something we've discovered or is it something we've constructed to look at the world? The sine waves really appear to exist in nature. Anytime we have constant speed and a repeating cycle, music, light, machines, planetary movement, they all follow lovely sine waves, providing we have a constant speed. Cos and tan are just different ways of looking at sine. You can make any complex wave or music by mixing sine waves. Any complex wave you can deconstruct into a set of sine waves. Apart from a sine wave, you can't deconstruct or simplify it. It is what it is. Okay, that's the end of the show on this one. I hope it's been helpful, and I'll see you next time.